All right, welcome to part 2 for today's lecture on Newton's first law of motion. So in the previous video, we looked a little bit at the history of how people started looking into motion. We saw Aristotle was wrong with thinking about it in terms of the 4 elements, 5 if you count space. And then Galileo focused a lot on this idea of how things moved and not the why. And so with Newton, what he actually ended up doing is taking the how and the why and putting them together. Except for he took the correct how, not Aristotle's how. So 24 years after Galileo died, Newton had his 3 laws of motion, which were heavily based on Galileo's experiments. And so this is something we're going to see a lot happening in this class is somebody does a lot of the groundwork. A second person, either their student or somebody who studies their work a couple years later, comes by, is like, oh, that's how that works, and then gets a huge majority of the credit, right? They're not called Galileo and Newton's laws of motion. They are called Newton's laws of motion, even though Galileo did a lot of the pre-work part for these laws. And so with Newton's laws of motion, at the very end, we're going to talk about some rules, but we can really use these for pretty much everything we interact with on our day-to-day life. So, we're going to talk about quantum mechanics a little bit later. We saw it pop up on one of those scale images where it says, you could use it for everything. You don't have to use it for everything. In the case of what we're going to be covering with Newton's laws of motion, the stuff we deal with on a day-to-day basis, it's really, really good for us. So, let's talk about Newton's first law of motion, which is sometimes also called the law of inertia. And we'll talk about what the word inertia means in a moment. But Newton's first law of motion states that every object continues in a state of rest or uniform speed in a straight line unless acted on by a non-zero force. There is a lot more to Newton's first law of motion than what Galileo originally stated, right? Galileo's original statement was constant speed in a straight line unless it's, interfered with. So now we have a more clear definition of what interference is. It is a non-zero force. So it's this non-zero force that we need to be aware of. So this was our interference. And now with Newton's first law, it still has the same uniform speed in a straight line. So this was from Galileo. But now it's added a little bit more. It's added this state of rest thing. A state of rest is our object is not moving at all. So right now, it's possible you are just sitting on a chair, couch, bed, laying down, whatever. You're probably not moving around much. If you laid or sat completely still, that would be considered being at rest, right? We're not worrying about the all individual parts inside. The net shape of you is at rest. And you would continue to stay at rest until something acts on you. So if you go outside and you stand still, you can be as still as possible for some amount of time Wind can come by and it can disturb your hair. Maybe you're standing there holding the leash on your dog and your dog decides it's time to move on from where you are, right? The dog can pull you, can have a non-zero force by pulling you in a direction. There's a lot of situations where you can have a non-zero force on the object. So as soon as it happens, right, you have a different situation than Newton's first law of motion. So there's a couple other ways you might see Newton's first law of motion mentioned. For example, you might see an object at rest likes to stay at rest. And, that's half right, because we need to make sure that we keep the uniform speed in a straight line as well when we're discussing Newton's first law of motion. So it's really got 4 key aspects in Newton's first law of motion. It is a state of continuation. We can either not be moving at all or moving in a straight line at a constant speed. And we have to have in order for this to continue happening, we must have zero force acting on us. So it doesn't mean no forces at all. It means something a little bit more complicated than that. So let's continue looking at Newton's first law of motion. There's the object at rest stays at rest part. I will move the Galileo portion. Give me a second. There we go. So an object at rest stays at rest is a really common way we can see Newton's first law of motion written, but it is not a complete picture. So let's just quickly go over some vocabulary because it's a really key aspect of what we're talking about. So Newton's first law of motion might also be called the law of inertia. And so what inertia is it is the resistance to a change in motion. And we're going to talk about inertia again a little bit later in the semester, but the more inertia an object has, it's going to resist motion more. So if you think about objects inside of your house, there's going to be some stuff that's really easy to move, right? You can probably move your phone around with relative ease. However, if you try to move your refrigerator, you're going to have to put in some more effort. So they have different amounts of inertia because of how easy or hard it is to get the object to move. Now, speed is something we're going to talk about again in our next lecture, but speed is the change in distance divided by the change in time. And what it really is, and how we think about it in our day-to-day lives, is just how fast the object is going. So when you're taking a walk, slowly strolling around, you have a certain speed. When you're in your car, all of you are good students, I firmly believe that, you're going this speed limit, right? You're going, depending on where you are, if you're on the freeway, you're going 65 miles an hour. The crazy people on the freeway, they're going 85 plus miles an hour, right? All of those things are related to speed, so just how fast you're going. So in context to Newton's first law of motion, speed is just going to be the same value. So if you're going at 65 miles an hour, you've put your car onto cruise control, and it's just going to keep going at 65 miles an hour. That's kind of what the goal is for trying to keep speed the same in relation to Newton's first law of motion. So this is 2 of the things. The other thing we need to focus on is this non-zero force aspect. And so in our day-to-day lives, with pretty much everything, we're going to encounter a force that eventually slows down and stops our object, right? We don't always have the luxury of looking at Newton's first law of motion, especially in the straight line at a constant speed situation. Newton's first law of motion, when we deal with it in a majority of cases, is because objects are stationary. We don't really see the straight line at a constant speed part because of this force that slows down and stops our objects, which is going to be friction. So friction just comes from this idea, and by idea it's a real thing, that our objects aren't actually perfectly smooth. So if you look at certain things, like if you go out and look outside in your backyard, it might be a little bit easier to see. So, for example, roads. Roads have potholes, they have, marks in them where people have somehow dug up part of the road. They're going to be a little uneven. They might have tire ruts in them if the road is really old. If you look at kind of a gravel path, you can see where people tend to walk. There's a lot of situations where, things aren't perfectly smooth. And so the way that we could start observing Newton's first law of motion in our day-to-day lives, where something is moving at a straight line, or in a straight line at a constant speed, we would need low friction situations. So for example, I personally am not one of these people, but if you know how to ice skate, right, you can glide along the ice for a pretty good amount of time before you would eventually glide to a rest. It's because you're going to have low friction in that situation. If you took the kind of the similar idea, so if you took ice skating versus either rollerblading or roller skating, right, you're not going to be able to slide as far rollerblading or roller skating because the friction is going to be much higher between your wheels and whatever ground you're on. But if you're on different types of ground, right, if you're trying to practice in a parking lot versus if you're on a nice smooth wooden skating rink, how you experience how often you need to put in effort to continue moving is going to be different. And so, like I said, there's a lot of situations where we're close, but we're still never going to quite be at moving in a straight line at a constant speed, unless somehow we can deal with this friction part of our motion. So a little bit more vocabulary, because we're going to now kind of work into what this zero force thing is this idea of net force as well as vectors. So a net force is just literally taking all of the forces acting on our object and adding them up. If we get 0, that means we would have Newton's first law of motion. If we get a non-zero number, something we'll see a little bit later is we'll have Newton's second law of motion. And so we'll talk about how to do net force a little bit later in the video. But the key thing we need to think about for forces is they are what is known as a vector. So in math and in physics, a vector is an object that has magnitude as well as a direction associated with it. So a magnitude is just a numerical number. And the direction tells us where that number is interacting with. So the way we're typically going to be seeing forces represented and how any vector is represented is an arrow. So this arrow here is a vector. It has some length value and it's pointing in a direction. So this is how we are going to represent our vectors. And force is a vector. So when we have our objects, we're going to have arrows sticking out of them. They'll have values. And we just need to make sure that we deal with it appropriately. Should put is instead of equals. So there's one other thing we need to talk about for vectors in order for us to kind of understand how they're working. So when I say opposite directions, what do you think of? So if I say right, what is the opposite direction? It's left. If I say the direction is down, its opposite direction is up. If I say forward, the opposite direction is backwards. And so it's going to be really important because if we move left and right, we're not moving forward and backwards or up and down. We're just moving left and right. And I can do that with all of the direction pairs I've talked about. So with vectors, we need to think about what direction stuff is moving in. So we're going to keep left, oops, it's helpful if I spelled left right, left and right together, up and down, forward and backwards. And we need to keep these pairs. So if something is moving left, the only other direction I'm going to have to think about is right. Those are the two directions that interact with each other. If I'm moving up and down, those are the only two directions that are interfering with each other. If I'm going forward and backwards, those are the only two interactions or directions that I'm working with. So I want to keep my pairs together when looking at net force. So let's kind of keep working on this idea of net force and vectors until we get to a mathematical example. So here I have a video. Yes, it is not a real video, but basically in this video, we technically have Newton's first law of motion acting on these candlesticks. And so for those of you who haven't seen this video, the Pope pulls this, I don't think it's technically called a tablecloth, but tablecloth from under these candlesticks, and they stay stationary. Let's see if I can get this to play. All right, cool. So he comes in, places some flowers, grabs it, pulls, they wiggle a little bit, but he has, right, he's holding the tablecloth. And so with that, right, we have, there's some weird force stuff going on. So we can have Newton's first law of motion happening in some really weird situations. If you want to see a more kind of detailed explanation as to what happens there and a more Mythbusters view on it, I'd recommend checking out this video down here. Also, again, just want to make it clear, the Pope did not actually do that. So let's talk about Newton's first law of motion in some more detail. So Newton's first law of motion is sometimes referred to as mechanical equilibrium. So there's a lot of names for Newton's laws of motion, and that's because they're really important for a lot of different reasons. So with mechanical equilibrium, it's just a really important state of motion. And so this here is a representation of how we can write out Newton's first law of motion. So this big thing here is a sigma. It's a capital, it's a capital sigma. So this is a Greek letter. And basically what it means is we want to add up all of the forces, or add up everything, which in this case, we want to add up all the F's, which corresponds to forces. And in Newton's first law, we want that value to be equal to 0. If the sum of all forces is 0, we then have either our object at rest or our object moving in a straight line at a constant speed. So it's going to be our job to see whether or not Newton's first law of motion holds true for our particular situations. So if and when, because you will be seeing this on the next quiz, I would give you this equation and I would give you the notation that is relevant. I do not expect you to memorize any equations for this class. I want you to be able to use them because that's really what physics is about. Using the appropriate equation or equations, plugging in the correct numbers where they need to be plugged in. It's not about memorizing equations. So do not expect to memorize this. So we need to consider, because force is a vector, we need to think about if the force is pointing and what direction it is, to be positive or negative. Because if we only have positive numbers, we can add as many numbers as we want up together. If they're all positive, they're never going to be 0. We can take all negative numbers and we can add all of these together. If we add them up, they're never going to be 0 as well. So we have to have positive and negative values associated with our objects in order to correctly find a net force equal to 0. And in order for us to get to 0, we must have 2 or more forces. One number by itself, unless it's 0, is never going to be equal to 0. So let's talk about traditional sign conventions. So in this class, I am going to be using the traditional type of signs in this case. So that is something that we are going to be doing. So let's look at left and right first. Right, so this is just 2 arrows. I have one pointing to the right and the other one is pointing to the left. Normally, we like to say right is positive. And the reason we say right is positive is if we look at writing out our numbers, we'd have 1, 2, 3, 4, etc. Right? They get bigger and they are all written as positive numbers. Because right is positive, left has to be negative. And that is just the way we're going to be using signs in this class. We're always going to say to the right is positive and to the left is negative. We can do the same type of sign check for up and down. So here we have an arrow. We have part of it pointing up and we have part of it pointing down. So with up and down, typically we like to think about this in terms of a building. Right, so we have our building and it has all of its floors. Right, so this is the first floor, the second floor, the third floor, the third, fourth, and fifth floor. So they go, as we move up the building, we increase the number of floors. So up is going to be our positive direction, and down is going to be our negative direction. So this is how we are going to be using signs in this class. If a force points right, it's going to be positive. If it points left, it's going to be negative. If it points up, it's positive. If it points down, it's negative. However, to kind of help us make sure that we don't mix our rights and our lefts with the ups and the downs, sometimes what you'll see in this class is I'll refer to the X and Y directions. So left and right is going to be X, and up and down is going to be Y. And this is just based on a standard coordinate system that math uses. And so this is also where we see right being positive, up being positive, left is negative, and down is negative. So for those of you who, I know some are a little bit more comfortable with math, this is a way we can remember our sign convention. For those of you who are not, we can use, the stories of a building, and in, our society, to the right is an increasing number of numbers. So this is going to be what we are using in this class to help us make sure we can add up all of our forces to equal 0. So here we have some examples. So here we have a box. It has some applied force acting on it. We want to go through and add up to the net force. So we want to set up our net force, and then we want to find the value of the net force. So what I'd like you to do is I'm going to do the first one, and then I'm going to want you to pause the video and try to do the other two boxes on your own. So if I look at my boxes, I'm only dealing with left and right. So that means that when I am doing all of my information, I'm going to be using the situation where to the right is positive and to the left is going to be negative. And because I want to find the net force, I want to add up all my force values. So if I look at this top one here, I have 2 forces. So there's a couple of different ways you can go about doing it. You can do all the negative ones first, and then do all the positive ones. You could do all the positives, then all the negatives. Either way is okay. I like to start at the top if there was anything here, and I like to work my way around clockwise. Doesn't matter as long as you make sure you count all of the forces on our object. So we now need to calculate the net force for this top one. So if I do that, I have a positive 10 and I have a negative 10. So I have plus 10 because I have 1 plus 10 force to the right, and I have minus 10 because I have a 10 force to the left. So this is going to be how I set up my net force. Positive 10 minus 10 is going to give me a value of 0. Oops. Yeah, so I have a value of 0. Let me just get this out of the way. So the net force in this case is going to be 0, so I realize I've made myself a not very fun one. So we'll just do this one for, let's just number these 1, 2, 3. So 1, I have positive 10 minus 10 equals 0. So that means that the forces for my top one cancel out, and I would have Newton's first law of motion being applied to this top box. So now what I'd like you to do is pause the video and go through and do the same type of analysis for the second and the third boxes and calculate the net force value. Okay, so let's look at the second box. I need to add up all of my forces. So if I look at my box, I have 2 arrows pointing to the right. So they're both going to be positive. I have nothing pointing to the left, and they both have a value of 10. So I'm going to have positive 10 plus 10, which is going to be a positive 20 value. So in the case of example 2 here, I do not have Newton's first law of motion, right? Because I have a non-zero force acting on my box. Now I want to look at number 3 here. So I have 10 pointing to the left, so that's going to be negative 10, and I have 8 pointing to the right, and so that's going to be a positive 8. So again, I like to just do it in whatever order we want, as long as we make sure we account for all of our objects. So negative 10 plus 8 is going to give us minus 2, which means our net force is going to point to the left with a value of 2. So this is how we can go through and talk about finding whether or not we have Newton's first law of motion. Is we can just make sure we add up all the forces and then go through, and if it's 0, boom, that's the first law. If it's not 0, like I said, what we'll look at next time, or not next time, next week, I believe, is the second law of motion. So there's just a couple other little things we're going to talk about for today's video. So one of them is this thing called the support force. So the support force is just a force that opposes gravity. You have gravity acting on you at all times because you're on Earth. And so gravity pulls you towards Earth, but you're not, last I checked, none of you have ever been to the center of the Earth. If gravity always was able to pull you in, humanity would be Well, we'd melt in the Earth's core. So there's something that opposes that, and that is the support force. So it's just some support, or it's just a force that opposes gravity. So here in this book, we have gravity, and this upward arrow is our support force. And basically, it comes from this way of how we look at matter and how we look at objects that are interacting with each other. And we're going to explore that later in the semester. Right now, we just want to acknowledge that this force exists. And if you're leaning on something or you're sitting on something, that deformation of your skin comes from the support force. And so the last thing we want to do is just really quickly cover a limitation. So we cannot always use Newton's first law of motion. And that's if we're changing speeds or we're changing directions. So in a situation of where we're in our car and we're going around a turn, we technically cannot use Newton's first law of motion. And we're not going to be able to explain why that's the case until we get into a little bit more terminology that we're going to be discussing in our next lecture, which goes over some terminology related to Newton's laws of motion. So right now, just understand we cannot always use Newton's first law of motion. Okay, so this is going to wrap it up for today's lecture. Please make sure, if you haven't already, to take the lecture quiz. And if you have any questions, let me know.